You settle into a quiet awareness, letting the steady rhythm of your own heartbeat become a reference for the passage of moments. Around you, the universe stretches in all directions, vast and unhurried, yet structured with a precision that can be measured. Time is one of these structures, not something that flows like water, but a coordinate, a dimension along which events are ordered. You sense that just as you can move north or south, east or west, you also move forward along this dimension, one instant after another. The science of time begins here, not in mystery, but in the meticulous observation of motion and change. You observe a simple pendulum swinging in a quiet room. Each swing marks a consistent interval, and centuries ago, people discovered that by counting these swings, they could track time with remarkable accuracy. Later, they refined these measurements using mechanical clocks, each tick a small, reliable beat marking the progression of seconds, minutes, and hours. You notice that what defines a second is now based on the vibrations of cesium atoms. The cesium-133 atom oscillates precisely 9,192,631,770 times to define 1 second. Every clock built to this standard is synchronized with atomic regularity, and you feel the universe's rhythm reflected in these tiny oscillations. You turn your attention to the skies. The planets follow their orbits in patterns that have persisted for billions of years. By observing their motion, astronomers can define years, months, and days. Earth's rotation and orbit provide a natural calendar, though ever so slightly irregular due to tidal forces and gravitational interactions. Yet, even these irregularities are predictable, measured, and accounted for. You sense that time is not an abstract concept but a framework grounded in repeatable events, a structure scientists can quantify and compare across distances and scales. You consider the principle that time is entwined with space. Einstein's theory of relativity redefines the way we understand temporal flow. Time is not an absolute universal measure, ticking identically for everyone, everywhere. Instead, it forms a continuum with space, a fabric called spacetime. You gently explore the idea that movement through space influences movement through time. For an object moving rapidly or positioned near a massive body, time passes differently than for an observer at rest in a weaker gravitational field. You find this concept reassuring in its predictability, founded in equations that have been tested with extreme precision. Atomic clocks flown on high-speed aircraft or placed in orbit confirm these effects. You imagine a clock on a plane circling the Earth while another remains grounded. The airborne clock ticks slightly slower, an effect called time dilation. These tiny differences accumulate over hours and days, measurable by scientists with extreme precision. Similarly, a clock placed near the surface of Earth, where gravity is slightly stronger, ticks slower than one farther away. You sense that these phenomena, subtle yet measurable, reveal a universe in which time is flexible, but fully governed by physical laws. You gently follow the logic behind these observations. The Lorentz transformation, a mathematical relation in special relativity, predicts how time and length adjust for objects in motion. You do not need to perform calculations yourself. It is enough to know that every experiment aligns with the predictions, confirming that the nature of time is not merely philosophical, but empirically grounded. You notice how this clarity creates a calm certainty. Time may stretch or contract, but it never behaves randomly. The universe is orderly, and you can trust the measurements. Looking around, you think of cosmic time markers. Pulsars, spinning neutron stars, emit beams of radiation at highly regular intervals, functioning as distant lighthouses of temporal consistency. Their pulses are so regular that they rival atomic clocks in precision. Observing a pulsar, you feel the immense scales of time across the galaxy, each pulse a silent heartbeat of a star that has lived for millions of years. You realize that measuring time in this way connects you to the universe, letting you align your understanding of moments with celestial phenomena. You notice that even light provides a method of measuring time. Light travels at a constant speed in a vacuum, and the distance it covers over time defines intervals on a cosmic scale. A light year, the distance light travels in 1 year, becomes both a measure of distance and a reflection of the time taken to traverse that distance. You imagine receiving light from distant stars that left their source millions of years ago, and you recognize that observing this light allows you to peer back into the past. Each photon carries a record of the moment it departed, preserving an exact measure of time elapsed. You reflect on the precision of measurement instruments on Earth and in orbit. Satellite navigation systems, for instance, rely on synchronized atomic clocks to triangulate positions with extreme accuracy. Even a tiny discrepancy in timekeeping would result in large errors in location. Engineers correct for time dilation effects due to both the satellite speeds and their positions in Earth's gravitational field. You sense that the everyday devices you use to navigate your world are subtle reminders of the deep connection between motion, gravity, and the passage of time. Your mind traces the logic of temporal measurement further, considering experiments in particle physics. Particles accelerated near light speed experience measurable time dilation. Muons, unstable particles created in the atmosphere, survive longer when traveling at high speeds than they would at rest. Observing this, you see a consistent pattern. Time is not a fixed backdrop, but a dimension shaped by the universe's physical structure. Every experiment you consider reinforces a tranquil understanding of temporal mechanics, and the predictability of these effects brings a calm rhythm to your awareness. You begin to perceive the dual role of time as both a personal and universal measure. Your own perception of seconds, minutes, and hours flows steadily, guided by biological rhythms. At the same time, the universe operates on scales both immense and minuscule, where time is tracked by atomic vibrations, pulsar rotations, planetary orbits, and cosmic expansion. You feel a sense of harmony in knowing that these scales coexist, all measured through the same underlying dimension. Time is reliable, measurable, and deeply consistent across contexts. You pause to observe how science conveys these truths. Equations and measurements are not abstractions. They are tools that capture reality with astonishing fidelity. By following the results of repeated experiments, by measuring the motion of clocks, atoms, and planets, you come to appreciate the universality of time. Each tick, each pulse, each orbit is a testament to the structured flow that underpins all events. You feel a quiet wonder at the coherence of these systems, a natural calm in the knowledge that time is orderly, measurable, and predictable. Your awareness extends to the practical ways humans navigate this dimension. Calendars, clocks, and time signals allow societies to synchronize activities, from the launch of spacecraft to the timing of experiments. You notice that all these systems are grounded in observable phenomena, from the vibrations of atoms to the rotation of Earth. There is no guesswork, only carefully verified measurements repeated over decades and centuries. Each moment you experience is part of this vast, interconnected temporal framework. Finally, your attention drifts to the subtle ways speed and gravity influence the pace of time. You consider that even though differences are tiny in daily life, they are essential for understanding the universe. The flexibility of time is not a threat to certainty, but an invitation to observe carefully. You feel the calm of knowing that every effect is measurable, predictable, and consistent. Time, in all its dimensions, is both personal and cosmic, offering a gentle, precise structure to every experience. You rest with the awareness that time is a coordinate you move along, shaped by speed, gravity, and the cosmic order. Its flow is measurable, its effects predictable, and its structure woven into the universe with exquisite precision. The universe preserves these records, from atomic oscillations to pulsar rotations, creating a steady rhythm that guides both matter and life. In this quiet understanding, you begin to sense the curious ways relativity will shape the experience of moving through space and the subtle stretch and contraction of moments around you. You begin by turning your attention to the precise structure of spacetime, where space and time are intertwined. In your mind, you picture a grid extending infinitely in all directions, each point representing both a location and a moment. Einstein's theory of special relativity tells you that movement through space affects movement through time. The faster an object moves, the more its passage through time slows relative to an observer at rest. This is not imagination. It is an effect measured repeatedly in laboratories and in space. You sense that motion and time are linked in a precise, measurable way. You reflect on the speed of light, constant in all frames of reference. No matter how fast you are moving, light travels at exactly 299,792,458 meters per second. This constancy underpins the equations of special relativity. You notice that it requires a revision of everyday assumptions. Simultaneous events are not simultaneous for all observers, and distances contract along the direction of motion. These effects are imperceptible at the speeds you experience daily, but they emerge clearly at velocities approaching that of light. You let your mind rest on this realization, appreciating the subtlety and predictability of nature's laws. Experiments with atomic clocks provide tangible evidence. Clocks on jets or satellites moving at high speeds tick more slowly than clocks on the ground. You imagine a pair of synchronized clocks, one on Earth and one aboard a jet circling the globe. After several hours, the airborne clock lags slightly behind its counterpart. These discrepancies are small, often measured in billionths of a second, but they demonstrate the tangible reality of time dilation. Satellites in the global positioning system must account for both this effect and gravitational time dilation to maintain positional accuracy. You perceive how relativity is not abstract theory but practical science embedded in technology. Gravity also influences time, as revealed by general relativity. Massive objects bend spacetime, causing clocks nearer to them to run more slowly than those farther away. You imagine standing near the surface of Earth and watching a clock far above in orbit. The difference is minuscule, yet measurable with modern atomic timekeeping. This phenomenon has been tested in laboratories, using precise instruments to detect tiny variations in the flow of seconds at different heights. You feel a sense of calm knowing that these effects, although invisible to the naked eye, are real and predictable, a consistent feature of the universe. You gently explore the famous thought experiments Einstein used to illustrate these ideas. Consider a twin traveling near the speed of light while the other remains on Earth. Upon returning, the traveling twin will have aged less. This is not speculation. Particle accelerators demonstrate analogous effects. Particles moving at extreme speeds decay more slowly than their stationary counterparts. These observations confirm that time's flow depends on both motion and gravity, reinforcing a coherent understanding of the universe's temporal framework. Light provides a natural reference for observing relativistic effects. Pulses of laser light in laboratories can measure minuscule differences in time and distance, revealing both length contraction and time dilation. You notice that even small, controlled experiments replicate the same effects predicted by theory on cosmic scales. Observations of binary pulsars, for instance, show variations in pulse timing consistent with predictions from general relativity. You let your mind absorb that the universe operates with a harmony that can be measured precisely, whether in a laboratory or among stars. You consider the mathematical structure behind these phenomena. The Lorentz factor quantifies how much time stretches or contracts for a moving observer. You do not need to solve the equations yourself. It is enough to recognize that every experiment matches these predictions. The universe behaves as the equations describe, and scientists have verified these results to extraordinary precision. This certainty provides a gentle reassurance, grounding your understanding of time in both theory and observation. Gravitational time dilation has practical consequences in space exploration. Spacecraft orbiting planets experience time slightly differently than clocks on the planetary surface. Engineers account for these differences when synchronizing communications and navigation. Even slight discrepancies can affect mission outcomes, which is why the understanding of relativity is crucial for precision in space operations. You notice how these small but measurable effects bridge theory and application, demonstrating the interconnectedness of fundamental physics and human endeavor. You think about extreme cosmic examples. Near a black hole, time slows dramatically relative to distant observers. Matter approaching the event horizon appears to move more slowly, and signals emitted from near the black hole are stretched in time. Astronomers detect this gravitational redshift when observing light from such regions. These observations confirm general relativity in the most extreme environments, showing that time is not a universal constant but a dimension shaped by mass and motion. You feel the tranquility of knowing that even these immense forces obey predictable laws. You imagine traveling near a neutron star, where gravity is incredibly intense. Clocks close to the star tick significantly slower than those far away. Your mind considers the calculations, the precise adjustments astronomers must make when interpreting signals from pulsars or high-energy phenomena near such stars. You sense the universe's consistency, a system in which even dramatic gravitational effects are orderly, measurable, and predictable. This realization brings a calm understanding of time's malleability under physical law. You reflect on the way scientists measure these effects in practice. Atomic clocks in laboratories, space missions, and orbital satellites provide a continuous dataset of temporal behavior. High-precision experiments confirm that time dilation is not hypothetical but an intrinsic feature of spacetime. You appreciate the meticulous effort required to measure and confirm these phenomena, reinforcing the certainty and elegance of relativistic physics. Time is flexible, but never random, shaped consistently by speed and gravity. Your awareness extends to the subtle interplay between relative motion and gravitational influence. Even in everyday life, these effects are present, though imperceptible. For instance, the GPS system on your phone requires constant correction for relativistic effects to maintain accuracy. You realize that your daily routines are subtly guided by these principles, and the predictable behavior of time in motion ensures the technology functions reliably. The calm order of the universe permeates both cosmic and human scales, linking you to the rhythms of spacetime. You contemplate the broader implications. Time is not an absolute backdrop but a measurable, dynamic dimension that responds to motion and mass. Each observation, from atomic vibrations to the orbits of satellites, confirms the intricate but predictable structure of spacetime. Your mind rests in the quiet certainty that time, while flexible, is governed by reliable laws that have been tested and verified extensively. This understanding allows you to observe the universe with clarity and curiosity, appreciating the precise dance of matter, motion, and temporal flow. As you absorb the elegance of these principles, you sense that time's flexibility opens a pathway to understanding deeper cosmic phenomena, including the ways gravity and motion influence the very structure of space itself, creating patterns and effects that shape the universe on scales both near and far. You begin by settling into the quiet awareness of measured time, recalling that motion and gravity shape the passage of moments. Imagine an astronaut aboard the International Space Station, orbiting Earth at nearly 28,000 kilometers per hour. For the astronaut, seconds, minutes, and hours tick steadily on a wristwatch, appearing normal from their perspective. Yet, for someone observing from Earth, those same seconds pass slightly differently. Atomic clocks on board the station and on the ground confirm this subtle divergence. You notice how these tiny differences, though imperceptible in daily life, demonstrate time's malleability under real conditions. The effect is measurable and predictable. Over a 6-month stay aboard the station, an astronaut ages only milliseconds less than someone on Earth. You picture scientists tracking this with atomic precision, using cesium-based instruments to record elapsed intervals. The data aligns perfectly with predictions from special and general relativity. You sense that even in this controlled environment, the universe communicates its temporal rules clearly, and human instruments are precise enough to detect them. Each observation reassures you of the consistency of time under varying conditions. You expand your awareness to faster speeds. Particles in accelerators approach a significant fraction of light speed, and their behavior provides direct evidence of time dilation. Muons, subatomic particles created by cosmic rays in the upper atmosphere, normally decay in microseconds. Yet, when traveling near the speed of light toward Earth, they persist longer than expected. Detectors at the surface record these particles, confirming that motion slows their internal clocks. You understand that time is not uniform, but relative to speed, a concept that is verified in controlled, repeatable experiments. You reflect on gravity's role in time dilation. Clocks placed at different altitudes show tiny, measurable differences in elapsed time. Experiments conducted atop mountains versus sea level reveal that clocks at higher elevation tick slightly faster due to weaker gravitational influence. Even variations of a few meters can produce detectable changes using modern atomic clocks. You notice how every element of this system, from motion to gravitational field strength, contributes to the measurable progression of time, producing a coherent and predictable pattern across multiple scales. You imagine the precise work of engineers maintaining satellite systems. Global Positioning System satellites, orbiting at altitudes of about 20,200 kilometers, experience time differently than clocks on Earth. Their onboard atomic clocks tick faster due to reduced gravity but slower due to their orbital velocity. The combination of these effects results in a net gain of microseconds per day. You see that engineers must account for these corrections continuously to provide accurate location data. Each calculation relies on an intimate understanding of how time varies with motion and mass. You turn to pulsars as cosmic examples of precise temporal markers. These neutron stars rotate at steady rates, emitting electromagnetic pulses with remarkable regularity. Observations of pulsars in binary systems reveal variations in pulse timing consistent with time dilation from both their orbital motion and gravitational fields. You notice that scientists interpret these variations using general relativity, providing a vast, natural laboratory for studying temporal effects. The universe itself offers examples of time dilation on scales far beyond human-made experiments, and you feel the calm precision of its laws. You consider how astronauts experience both effects simultaneously. Orbiting Earth, they move at high velocity while being slightly farther from the planet's center of mass. Special relativity predicts that motion slows their clocks, while general relativity predicts that weaker gravity speeds them up. These effects partially cancel, but careful measurement confirms the precise balance. You sense the beauty of this exactitude. The laws of physics interact consistently, producing outcomes that can be calculated and observed without ambiguity. This reassurance allows your mind to rest in the predictability of the cosmos. You imagine standing on Earth and watching a clock fly overhead on a high-speed aircraft. From your perspective, the airborne clock ticks more slowly than one beside you. From the pilot's perspective, their own clock ticks normally, while the earthbound clock appears to move more slowly along their path of motion. You notice how the relative perspective alters measurements without contradicting the underlying laws. Time is not absolute. It is a quantity measured differently depending on speed and gravitational context. The universe maintains its coherence, and your awareness aligns with this certainty. You follow the logic further into particle physics laboratories. Experiments with fast-moving ions and subatomic particles consistently show that moving systems experience slower decay rates. Storage rings keep particles circling at high velocity, and scientists measure their lifetimes extending as predicted by relativity. These controlled observations provide direct, repeatable evidence for time dilation at scales far removed from human perception. You appreciate that both microcosmic and macroscopic systems confirm the same fundamental principles, a calming reminder of nature's consistency. You consider how time dilation affects communication signals. Satellites transmitting radio waves to Earth experience delays and frequency shifts that must be precisely calculated. Engineers account for both motion-induced and gravity-induced effects to ensure signals remain synchronized. You notice that these corrections are crucial for maintaining technology that guides travel, trade, and scientific observation. The invisible influence of time dilation gently underlies much of the practical infrastructure you rely on, grounding abstract physics in everyday life. You imagine a traveler in a high-speed spaceship returning from a distant planet. The traveler's clock shows fewer elapsed seconds than a stationary observer on Earth. Even small journeys produce minuscule differences, and vast interstellar voyages would exaggerate these effects dramatically. You sense that relativity is not an obstacle but a framework that provides precise predictions, ensuring that temporal measurements remain consistent regardless of perspective. The universe is patient, keeping its rules steady and observable, allowing you to explore them calmly. You reflect on the combination of natural and human-made examples. From the decay of cosmic particles to the orbits of satellites, time dilation manifests predictably and measurably. Each observation reinforces that time is a dynamic dimension, responsive to motion and gravity yet orderly and consistent. You sense a quiet continuity connecting experiments in the laboratory to phenomena across the cosmos, forming a chain of evidence that strengthens your understanding. This calm realization anchors your thoughts in the reliability of physics. You rest with the awareness that time flows differently depending on speed and gravitational strength. Yet these variations are entirely measurable and consistent. Atomic clocks, satellites, pulsars, and high-speed particles all provide evidence for the flexibility of time. You feel the reassuring order of the universe, a system in which every movement, every gravitational field, and every measurement aligns with predictable rules. In this quiet certainty, your mind becomes receptive to the ways extreme environments and velocities will continue to reveal the subtle mechanics of temporal flow. You begin by envisioning spacetime as a continuous, flexible structure, stretching and bending in response to mass and energy. In this fabric, certain solutions to Einstein's equations suggest the existence of tunnels, connecting distant points in space and time. These hypothetical passages are known as wormholes or Einstein-Rosen bridges. You notice that they are entirely mathematical in origin, derived from the same principles that describe gravity and motion. Their possibility is not based on speculation, but on equations that have repeatedly been validated in countless other contexts. The concept arises naturally from general relativity. Massive objects warp spacetime, and under the right conditions, this warping could form a bridge between two regions. In theory, these bridges would allow travel between points that are otherwise separated by vast distances. You imagine tracing the geometry of such a bridge, seeing a tunnel connecting two sheets of spacetime. The mathematics predicts their shape, size, and connection to the surrounding fabric, though it also highlights the extreme constraints necessary for stability. You notice the first requirement for a traversable wormhole is the presence of exotic matter. This matter would have negative energy density and negative pressure, properties that differ fundamentally from the ordinary matter you encounter daily. Exotic matter is necessary to prevent the wormhole from collapsing under its own gravity. You sense the precision of this requirement, understanding that without it, the bridge would pinch shut before anything could pass through. Every solution, every calculation, reinforces the delicate balance needed to maintain a tunnel in spacetime. You consider the equations in more detail. Einstein's field equations describe how mass and energy influence the curvature of spacetime. By manipulating these equations under extreme conditions, scientists have derived solutions that correspond to wormhole geometries. You feel the calm rigor of the process. The mathematics is consistent, the derivation methodical, and the implications profound, yet they remain firmly within the domain of theory. You do not need to perform the calculations yourself to appreciate the exactness and predictability of these results. You gently explore the potential effects of traversing a wormhole. A traveler entering one mouth would theoretically exit at the other instantaneously or after a very short interval, depending on the relative positions and motion of the endpoints. The pathway would be far shorter than the distance through normal space. Yet, you notice that stability is fragile. The tiniest disturbance could cause collapse. The equations indicate that any practical use would demand precise control over energy and structure, far beyond current technological capability. You feel the reassuring order of the laws governing these extremes, consistent and reliable. You consider evidence from cosmic observations. No wormholes have been detected directly, and the observable universe shows no clear signature of such structures. Astronomers examine gravitational lensing and other phenomena for anomalies that might indicate the presence of tunnels, but so far, the data aligns with conventional models. You notice that this absence does not invalidate the theoretical solutions. It only emphasizes that if wormholes exist, they are exceedingly rare or require conditions unlike those naturally occurring near Earth or in nearby stars. You explore the question of scale. Theoretical models allow for wormholes of various sizes, from microscopic to enormous. Tiny, quantum-scale wormholes could exist at the Planck length, a dimension far smaller than atoms, but their effects would be imperceptible to human senses. Larger, macroscopic bridges require immense amounts of exotic matter to remain stable. You sense that the universe has a clear hierarchy of physical constraints, where extreme possibilities exist mathematically but may be practically unattainable. The order and consistency of these rules are calming, a steady framework underlying complex ideas. You imagine the energy requirements. Calculations indicate that sustaining a traversable wormhole would demand energies comparable to the mass energy of stars or even greater. This is not speculation. It follows directly from the mathematics of general relativity and the known properties of matter. You recognize that the universe permits such solutions in principle, yet imposes strict limitations. The interplay between possibility and constraint reassures you that even the most extreme phenomena obey precise, observable rules. You gently consider causality. If a wormhole were to connect regions with differing temporal coordinates, it could theoretically allow travel into the past or future. You notice that physics imposes limits to prevent paradoxes. Closed time-like curves, solutions in relativity that permit returning to an earlier time, are possible mathematically, but any practical scenario would require conditions so extreme that nature maintains overall consistency. You sense the universe's subtle protection of causality, ensuring that the flow of events remains logically coherent. You reflect on the distinction between theory and experiment. Wormholes are solutions derived from validated equations, yet none have been constructed or observed. You notice that science separates mathematical possibility from empirical reality. The calmness comes from understanding this distinction. The equations are reliable, and their implications are exact, but physical manifestation may lie far beyond current capability. Observing the cosmos, you find reassurance that theoretical predictions consistently match what can be measured, reinforcing confidence in the underlying laws. You think about smaller analogs in laboratory physics. Certain quantum systems exhibit temporary fluctuations in energy that could be loosely compared to miniature wormholes, but these effects operate on subatomic scales and dissipate almost instantly. You notice the value of these experiments in informing theoretical understanding, even if they do not produce macroscopic bridges. They demonstrate that spacetime is flexible in principle, and the laws governing this flexibility are precise and measurable. Your mind appreciates the interplay of observation and theory, each confirming the other. You consider the potential observation of distant wormholes. Light passing near a stable tunnel would bend in a specific pattern due to gravitational lensing. Astronomers monitor light from distant galaxies for distortions that cannot be explained by ordinary mass distributions. So far, observations fit conventional models. You feel the calm certainty of science. It measures carefully, predicts accurately, and interprets data based on established laws. Even the most exotic possibilities are subject to rigorous evaluation. You reflect on the conceptual clarity of wormholes. They exist as exact solutions within the framework of general relativity, constrained by the requirements of exotic matter, stability, and energy. Their existence is mathematically permissible, yet nature imposes stringent conditions. You notice that this balance between possibility and constraint is a hallmark of the universe's structure. Laws are exact, outcomes are predictable, and extreme scenarios are bound by precise physical principles. This recognition brings a quiet satisfaction, a sense of safety in the consistency of reality. You imagine the delicate geometry of a wormhole, the throat connecting two spacetime regions, held open by the required negative energy. Any fluctuation in that energy or structure could collapse the passage, illustrating the fragility inherent in such extreme configurations. You feel a calm understanding that while the universe allows theoretical extremes, it also enforces order, ensuring that even remarkable solutions follow strict rules. Observing these constraints deepens your appreciation for the predictability and elegance of physical law. You rest in the awareness that wormholes are a feature of precise mathematics, constrained by energy, stability, and geometry. They are theoretically possible but experimentally unverified, existing as a boundary between what the equations allow and what nature has yet to produce. You notice the calm certainty that underlies these extreme possibilities. Every calculation is grounded in real physics, and every requirement is measurable, even if not currently attainable. In this understanding, you begin to sense how extreme gravity, like that near black holes, will continue to reveal the ways spacetime itself can bend and shape time's flow. You begin by centering your attention on gravity, the force that governs motion and shapes spacetime. Black holes are regions where gravity becomes so intense that not even light can escape. They are the natural consequence of matter compressed into extremely dense volumes. You observe that their formation is the result of well-understood physical processes, from stellar collapse to the conservation of mass and energy. Despite their extreme nature, Black holes are fully consistent with the laws of physics, and their influence on time is both measurable and predictable. You imagine approaching a black hole from a safe distance. The space-time around it curves steeply, and as you draw nearer, time begins to behave differently. Clocks far from the black hole tick normally, while clocks closer to its event horizon run more slowly. This is a consequence of gravitational time dilation, predicted by general relativity. You notice that this effect has been observed in weaker forms near massive objects on Earth and in orbit, confirming the underlying principle. The more extreme the gravity, the more pronounced the slowing of time becomes. You picture a particle or beam of light falling toward the black hole. From a distant observer's perspective, its motion appears to slow as it nears the event horizon. The particle never seems to cross the horizon completely, its movement stretched across time. From the particle's own perspective, it crosses the horizon in finite proper time. You notice how relativity allows both observations to be correct simultaneously. The universe remains consistent, even when time behaves counterintuitively in regions of extreme gravity. You reflect on the mathematical description of black holes. Solutions to Einstein's equations, such as the Schwarzschild metric, describe non-rotating black holes, while the Kerr metric describes rotating ones. These solutions define the structure of spacetime, including event horizons, singularities, and the paths objects can follow. You sense the precision of these descriptions. Every quantity is defined by measurable parameters, from mass and spin to the curvature of space. These solutions provide a predictable map of what occurs near a black hole, despite the unfamiliarity of the environment. You consider the paths of light and matter near the horizon. Photons emitted outward are increasingly redshifted, stretching their wavelengths as they climb out of the gravitational well. You notice that signals sent from near the black hole take longer to reach a distant observer, and their frequency shifts can be calculated precisely. Astronomers detect this gravitational redshift in light from stars near compact objects. Observations match theoretical predictions with remarkable accuracy, providing empirical evidence for the relationship between gravity and time. You explore the concept of closed time-like curves. Certain solutions to the equations of general relativity, particularly near rotating black holes, permit paths that return to the same point in spacetime. These theoretical loops allow for the possibility of returning to an earlier moment along a world line. You notice that creating such conditions would require precise configurations of mass, rotation, and energy. The mathematics is exact, but nature imposes strict constraints, and these time loops remain theoretical rather than observed. You feel the calm reassurance that laws of physics maintain order even in extreme scenarios. You think about the singularity at a black hole's center. Here, the curvature of spacetime becomes extreme, and classical descriptions of time and space break down. Quantum gravity is expected to provide a more complete understanding, but for now, the singularity serves as a boundary of our current knowledge. You sense the quiet patience of science. The universe presents challenges, yet each limit is approached methodically, guided by observation and theory. Even the unknown is framed by what is measurable and consistent with physical laws. You notice how the interaction between rotation and gravity affects time. In a rotating black hole, frame dragging occurs, pulling spacetime along with the rotation. This effect causes orbits to shift and can influence the paths of particles near the event horizon. The calculations are exact, and predictions align with observations of spinning compact objects. You perceive that even in these extreme regions, the universe behaves according to precise rules, where motion, gravity, and time interact in predictable ways. You reflect on cosmic observations of black holes. Gravitational waves, detected from merging black holes, confirm the dynamics of spacetime under extreme conditions. The timing, amplitude, and frequency of these waves match theoretical predictions. You notice that these measurements, taken from millions or billions of light-years away, provide direct evidence of time and space behaving as relativity predicts. The universe consistently validates the theories describing these powerful objects. You consider the practical implications for observers. If a spacecraft approached a black hole without crossing the horizon, the crew would experience time differently from people far away. Minutes for those near the horizon could correspond to years for distant observers. You imagine the precision required to calculate trajectories and avoid hazards, understanding that relativistic effects are central to accurate navigation in strong gravitational fields. The predictability of these calculations reinforces the orderliness of physics. You follow the logic of how time loops are constrained. While the equations allow paths that return to the same temporal coordinate, energy conditions and stability requirements limit practical realization. Any small disturbance could prevent the loop from forming. This illustrates a consistent principle. Nature permits certain mathematical possibilities, but enforces limits that preserve causality and stability. You sense reassurance in this balance, appreciating that even extreme theoretical scenarios conform to rigorous rules. You examine the observation of matter accreting onto black holes. Disks of gas emit X-rays as friction heats them to millions of degrees. The timing of these emissions is influenced by both orbital motion and gravitational time dilation. Astronomers measure light curves and spectra to infer conditions near the event horizon. You notice how these observations allow scientists to probe the behavior of time in extreme gravitational fields with high precision. The universe communicates its rules, measurable and consistent, even in the most intense environments. You think about the interaction of black holes with their surroundings. Stars orbiting close to a black hole exhibit predictable accelerations and shifts in spectral lines due to gravitational time dilation. Observing these stars provides a natural laboratory for testing relativistic effects. You feel the calm assurance that physical law extends consistently from laboratory scales to cosmic distances. Every observation fits within a coherent framework, confirming the reliability of theoretical predictions. You reflect on the subtle lessons of these extreme conditions. Time slows near massive objects, yet this behavior is fully predictable and measurable. Closed time-like curves exist mathematically, but practical realization is constrained by energy and stability. Observations of accretion disks, orbiting stars, and gravitational waves provide continuous verification. You feel the gentle certainty that even in the universe's most intense regions, time is structured, governed by precise equations, and entirely consistent with relativity. You rest with the awareness that black holes reveal the flexibility of time under extreme gravity. The universe maintains order, enforcing causal consistency while allowing extreme variations in temporal flow. You notice that these conditions create natural laboratories, where motion, mass, and curvature interact in exact accordance with Einstein's equations. In this understanding, your mind opens to the ways cosmic clocks and space-time distortions provide evidence for the subtle, measurable mechanics of time itself. You begin by centering your awareness on the vast timescales of the cosmos. Unlike the seconds and minutes you experience daily, cosmic time stretches across billions of years. You notice that the universe itself carries its own markers of temporal progression. These markers, like the rotation of pulsars, the decay of radioactive elements, and the expansion of space, function as natural clocks, allowing scientists to measure the age of stars, galaxies, and the universe itself. You sense the calm precision inherent in these measurements, grounded in observation and verified through multiple independent methods. You first observe pulsars, spinning neutron stars emitting electromagnetic pulses at remarkably regular intervals. These pulses act like cosmic metronomes, their timing so consistent that deviations can be measured in millionths of a second. Astronomers track these pulses to understand not only the star's rotation but also the effects of gravitational fields and motion on temporal measurement. You notice that pulsars provide a framework for observing time on scales far larger than human lifespans, yet entirely measurable and predictable. Their regularity is a gentle reminder of the order present even in extreme environments. You then consider radioactive decay, a process governed by the precise half-lives of unstable isotopes. Elements such as uranium-238 decay into lead-206 over 4.47 billion years, while thorium-232 and potassium-40 follow their own predictable decay schedules. Geologists and astronomers use these rates to determine the ages of rocks, meteorites, and planetary bodies. You imagine scientists carefully measuring the ratios of parent and daughter isotopes, each calculation reinforcing the constancy of natural laws. The reliability of radioactive decay offers a tranquil assurance that time's passage can be quantified accurately across billions of years. You shift your focus to the broader cosmos, where light from distant galaxies carries a record of the universe's expansion. Observations of redshift reveal that galaxies are receding from each other, a consequence of the stretching of space itself. By combining these measurements with the rate of expansion, known as the Hubble constant, scientists estimate the time elapsed since the universe began. You notice that multiple methods, including observations of supernovae and the cosmic microwave background, converge on an age of roughly 13.8 billion years. This convergence provides a calm, precise framework for understanding the universe's history. You explore the cosmic microwave background, CMB, the afterglow of the Big Bang. This faint radiation, uniform across the sky yet with subtle variations, offers a snapshot of the universe roughly 380,000 years after its origin. By analyzing temperature fluctuations and patterns in the CMB, scientists infer the density, composition, and expansion rate of the early universe. These calculations, combined with models of cosmic evolution, allow a precise determination of the universe's age. You notice that the CMB functions as a universal clock, recording a moment in time that can be measured billions of years later. You gently consider stellar life cycles as natural indicators of cosmic time. Stars evolve predictably based on mass and composition. Massive stars burn their fuel quickly, living only millions of years, while smaller stars like our Sun can shine steadily for billions. Observing star clusters with a range of stellar ages allows astronomers to estimate their formation times. You sense the calm rhythm in these life cycles, where each star follows a predictable sequence of stages: birth in molecular clouds, fusion-powered maturity, and eventual transition into white dwarfs, neutron stars, or black holes. These processes provide natural temporal markers across galactic scales. You reflect on the integration of multiple techniques. Combining pulsar timing, radioactive decay, stellar evolution, and cosmological expansion gives a coherent picture of time on cosmic scales. Each method corroborates the others, allowing scientists to reduce uncertainty and refine estimates of the universe's age. You notice how observation and theory reinforce each other, producing precise results that align with fundamental physics. The calm comes from knowing that time can be measured accurately, whether on the scale of atoms, stars, or galaxies. You imagine measuring time in the earliest moments of the universe. The period known as cosmic inflation occurred within fractions of a second after the Big Bang, causing space to expand exponentially. While direct observation is impossible, models constrained by CMB data and particle physics allow scientists to estimate durations with remarkable precision. You sense that even in these extreme early conditions, time is accessible to measurement through careful inference, linking the smallest physical processes to the largest cosmic structures. You consider the role of globular clusters, densely packed collections of old stars. By studying the brightness and color of stars within these clusters, astronomers determine their ages. Many globular clusters are found to be over 12 billion years old, providing a lower bound on the universe's age. You notice how these clusters function as stable, long-lived temporal references, allowing scientists to calibrate other methods. Observing them offers reassurance that time is consistent across space and observable over immense intervals. You reflect on the expansion of the universe itself as a clock. Space stretches, carrying galaxies with it. By measuring distances, redshifts, and the growth of large-scale structures, astronomers track the rate of cosmic expansion and estimate elapsed time since the Big Bang. This method connects directly with physical observations, producing an independently verifiable measure of cosmic age. You sense the calm reliability of these measurements. Each galaxy, each cluster, each distant signal aligns with predictions from general relativity and cosmological theory. You examine how time is verified through precision measurements in laboratories and observatories. Atomic clocks calibrate observational equipment, ensuring that measurements of pulsars, supernovae, and other cosmic phenomena are synchronized. These clocks provide a human-scale anchor for interpreting events billions of years old. You notice that connecting local, precise measurements to distant cosmic events requires careful application of physics, but the results are consistent and predictable. This integration of scales offers a gentle reassurance that the universe operates with universal order. You imagine tracing the light from a distant quasar, traveling for billions of years to reach your instruments. The information encoded in that light represents the universe at a moment long past. By comparing this signal to models of cosmic evolution, scientists deduce both the distance and the corresponding time interval since emission. You notice how time is encoded in observable quantities across vast distances, allowing measurement of the universe's age through careful analysis. Each calculation confirms the continuity and predictability of cosmic processes. You reflect on the interplay of natural and artificial clocks. Pulsars, radioactive isotopes, stellar life cycles, and cosmic expansion all provide evidence for the universe's age. Atomic clocks and observational instruments ensure consistency in measurement, linking human precision to cosmic scales. You sense the calm reassurance that comes from this alignment. Time, from the microcosm to the macrocosm, is measurable, consistent, and predictable. You feel a quiet connection to the vast temporal framework in which you exist. You rest with the awareness that cosmic clocks offer a precise measure of the universe's age. From the pulses of neutron stars to the afterglow of the Big Bang, from radioactive decay to the expansion of galaxies, time is recorded and measurable. You notice that these measurements provide continuity across scales and eras, establishing a tranquil certainty in the flow of cosmic history. In this understanding, your mind becomes open to the subtle ways time interacts with the structure and evolution of the universe itself, revealing the interconnectedness of space, matter, and temporal progression. You begin by turning your attention inward, toward the scale of atoms and subatomic particles. Here, time behaves differently than in the large-scale cosmos you have observed so far. Quantum mechanics provides a precise framework, describing the probabilities of outcomes rather than deterministic trajectories. In these equations, time functions as a parameter, marking evolution rather than an observable itself. You notice that this treatment of time is consistent and predictable, allowing calculations of particle behavior over intervals, even when the outcomes remain probabilistic. You consider the example of an electron in an atom. Its position and energy are not fixed, but represented by a wave function that evolves over time according to the Schrödinger equation. The evolution is continuous and mathematically exact, even if measurement collapses the wave function into a single outcome. You sense that time in this context is a dimension along which probabilities change, a clock guiding quantum events, precise and consistent, though manifesting unpredictably in individual measurements. You then explore superposition, where particles can occupy multiple states simultaneously. Experiments confirm that these states evolve coherently over time, until observation or interaction causes a collapse. You notice that superposition is fully described by time-dependent equations, where the sequence and duration of evolution are mathematically constrained. The apparent strangeness is not disorder but a well-defined set of rules applied to microscopic systems. You feel a calm understanding that these principles, while counterintuitive, are predictable and measurable. You examine entanglement, a phenomenon in which particles share correlated states regardless of separation. Measurements on one particle instantaneously influence the expected outcomes of its partner. Time enters the description as the sequence in which measurements occur, establishing correlations without violating relativity or causality. You notice that these experiments are conducted under controlled conditions, with timing precision measured in nanoseconds, allowing scientists to map temporal relationships in a fully consistent manner. The universe's rules remain intact even at this microscopic level. You gently consider the limits of causality in quantum mechanics. While individual outcomes are probabilistic, cause and effect are preserved in statistical predictions. You notice that delays, interactions, and sequence ordering are all accounted for in time-dependent equations. The theory ensures that events unfold in a manner consistent with temporal ordering, even when individual results appear random. This combination of probabilistic behavior and structured evolution reassures you that the flow of time remains orderly at microscopic scales. You reflect on delayed choice experiments, where decisions made in the present affect how previous measurements are interpreted. These experiments probe the relationship between time, measurement, and information in quantum systems. You notice that results are always consistent with the theory, No information travels backward in time, and causality is maintained. Time in quantum mechanics is a parameter that orders processes, ensuring predictability and coherence, even under the most subtle experimental conditions. You imagine observing a particle through successive measurements. Each interaction nudges its state, with the evolution between measurements governed by the time-dependent Hamiltonian. You notice that this evolution is deterministic mathematically, even if outcomes are uncertain. The interplay of probability and temporal structure creates a consistent framework, where predictions are reliable over ensembles of events. You feel a gentle assurance in the consistency of quantum time, bridging the microscopic world to macroscopic observations. You consider particle decay, another quantum process influenced by time. Unstable particles have well-defined lifetimes described by exponential probability distributions. Individual decay events are unpredictable, yet the overall statistical pattern is exact. You notice that time again functions as a precise parameter, guiding the probability of occurrence. Observations across many particles confirm these predictions with remarkable accuracy, reinforcing the structured behavior of temporal evolution in quantum systems. You reflect on tunneling, where particles traverse energy barriers in ways forbidden classically. Time governs the likelihood and sequence of tunneling events, calculable through precise equations. Experiments with electrons and other particles demonstrate exact agreement with theoretical predictions. You notice that even when particles behave counterintuitively, time provides an ordered framework for understanding, ensuring that all processes follow the same consistent laws. You examine the interplay of quantum mechanics with relativity. At high energies or in strong gravitational fields, time affects particle behavior more subtly, as relativistic corrections alter the evolution of wave functions. You sense that quantum and relativistic descriptions can be combined through quantum field theory, producing a coherent picture where time remains a measurable and well-defined parameter. The mathematical consistency reassures you that even extreme conditions do not compromise the order of microscopic events. You consider how temporal ordering is critical in quantum information experiments. Sequences of gate operations, measurements, and interactions must be timed precisely to achieve predictable outcomes in quantum computers. You notice that while the underlying processes are probabilistic, the temporal framework ensures coherent evolution. This demonstrates that time in quantum systems is both a guiding parameter and a structure within which probabilistic events occur reliably. You reflect on the connection between microscopic and macroscopic time. The statistical behavior of countless quantum events produces predictable outcomes at larger scales, bridging uncertainty to determinism. You sense the gentle flow from randomness to order, from individual particles to ensembles, and from quantum events to classical observations. Time serves as a continuous thread, linking micro and macro worlds, enabling precise prediction despite inherent uncertainty. You imagine the implications for understanding the universe. Quantum mechanics, with time as a guiding parameter, provides the foundation for particle physics, chemistry, and condensed matter. Experiments probing superposition, entanglement, and decay reveal that time, though subtle and flexible at small scales, maintains order and coherence. You feel the calm assurance that even at the smallest scales, the universe operates according to consistent principles, measurable and predictable within well-defined frameworks. You rest with the awareness that time at the quantum level is precise, ordered, and measurable, even as individual events remain probabilistic. Superposition, entanglement, tunneling, and decay all follow time-dependent rules that can be calculated and tested. You notice that this delicate structure underlies the behavior of matter, energy, and information, forming a foundation for all processes you have observed so far. In this understanding, your mind opens gently to the ways quantum time connects to causality, measurement, and the broader flow of the cosmos. You begin by centering your attention on cause and effect, the principle that underlies all physical interactions. In daily experience, causes precede effects, a sequence that appears consistent and reliable. Physics formalizes this through the concept of causality. Events are connected in a structured order, and violations of this order would create inconsistencies. You notice that causality is embedded in both classical mechanics and relativity, providing a framework within which time functions predictably, even when spacetime itself is curved or extreme. You consider the idea of paradoxes, often illustrated with hypothetical scenarios like the grandfather paradox. If one could travel back and prevent an ancestor from existing, a logical contradiction would arise. You notice that physics itself prevents such contradictions. The equations of general relativity, quantum field theory, and thermodynamics impose constraints that maintain consistency. Even theoretical constructs allowing closed time-like curves are subject to rules that preserve overall causality. The universe enforces order at every level, ensuring that events cannot unfold in ways that create contradictions. You explore the Novikov self-consistency principle, a theoretical framework suggesting that any events occurring along closed time-like curves must be self-consistent. Actions taken by a traveler along such a curve cannot alter history in a way that generates contradictions. You notice that this principle arises directly from mathematical consistency, not speculation. It allows time loops mathematically, but only those that maintain the integrity of cause and effect. You feel a calm reassurance in this idea, understanding that the universe's laws inherently protect logical order. You reflect on the role of energy conditions in preventing paradoxes. Exotic configurations that might allow backward time travel often require violations of energy constraints, such as negative energy densities beyond natural limits. These requirements indicate that physically realizable paradoxes are forbidden by nature. You notice the precise balance in physical law. Mathematical solutions may exist in theory, but the universe enforces boundaries that maintain causality. The principles are exact, consistent, and measurable, producing a framework in which logical consistency is preserved. You imagine a hypothetical traveler interacting with their own timeline. The laws of physics dictate that any actions taken must be compatible with what has already occurred. Attempts to change events that would create contradictions are mathematically suppressed or rendered impossible by stability constraints. You notice that these rules do not rely on conjecture. They emerge from the structure of spacetime itself, as described by Einstein's equations. The universe contains inherent safeguards against logical inconsistency. You consider quantum mechanics and its relationship to causality. While quantum events are probabilistic, the order of interactions remains well-defined statistically. Entangled particles exhibit correlations without violating causality. You notice that even when outcomes appear random, the sequence of cause and effect is preserved on average. The combination of relativity and quantum mechanics maintains consistency across scales, from subatomic events to macroscopic phenomena, ensuring that paradoxical contradictions cannot manifest in observable reality. You explore the idea of time loops in rotating black holes. The Kerr metric allows solutions that include closed time-like curves under extreme rotation. However, these curves exist only in regions shielded by horizons or singularities, inaccessible to external observers. You notice that physical accessibility is limited by these boundaries, preventing practical violations of causality. The mathematics shows possibility in theory, but physical laws enforce inaccessibility, preserving consistent timelines and preventing paradoxes from arising in any observable manner. You reflect on information flow in time. Signals and interactions propagate along well-defined paths within light cones, ensuring that effects cannot precede causes outside the allowed regions. You notice that relativity formalizes these limits, constraining the sequence of events to prevent contradictions. Even in theoretical scenarios with extreme gravitational or topological conditions, the propagation of information adheres to causality, maintaining the logical structure of spacetime. This constraint is precise and measurable, providing a foundation for all temporal processes. You examine the role of entropy and thermodynamics in reinforcing causality. Entropy increases over time in isolated systems, creating an arrow of time that aligns with the sequence of cause and effect. While microscopic processes may be reversible, macroscopic behavior produces a consistent directionality. You notice that even hypothetical time loops would need to respect this entropic ordering, ensuring that paradoxes do not violate fundamental physical principles. The universe integrates statistical mechanics with space-time structure to maintain a coherent temporal sequence. You consider experimental tests of causal order. Quantum experiments involving delayed choice and entanglement verify that correlations appear consistent with temporal ordering. No experiment has demonstrated a violation of causality, even when measurement sequences are manipulated. You notice that these results confirm the theoretical principles observed in general relativity. The universe preserves logical order, and temporal consistency is observable and reliable across a variety of scales. The precision of these tests provides reassurance that causality is fundamental, not contingent. You reflect on the distinction between mathematical freedom and physical reality. Equations may allow unusual topologies or time loops, but energy, stability, and observational constraints prevent paradoxical outcomes. You notice the gentle rigor of these safeguards. While imagination can explore hypothetical constructs, the universe ensures that measurable events remain consistent. You sense that this distinction is central to understanding time. Theoretical possibilities exist, yet physical reality remains self-consistent and orderly. You imagine the natural enforcement of causal integrity. Across quantum systems, stellar evolution, and cosmological expansion, every process adheres to structured sequences. Events unfold in ways that prevent contradictions, maintain logical order, and preserve consistent histories. You notice that this consistency is not arbitrary but a direct consequence of fundamental physical principles, mathematically derived and empirically confirmed. The universe operates as a coherent system, where time and causality are deeply intertwined. You rest with the awareness that paradoxes, while intriguing in thought experiments, are prevented by the universe's consistent laws. Causality is maintained by energy constraints, space-time geometry, and statistical mechanics. Theoretical frameworks like self-consistency principles reinforce these protections. You notice that the flow of cause and effect is preserved across scales, from quantum interactions to cosmic events, offering a calm understanding that the universe safeguards its own temporal integrity. You begin by focusing on laboratories, where time is measured and tested with extraordinary precision. Atomic clocks, for example, rely on the vibrations of cesium or strontium atoms, oscillating with predictable regularity. These clocks are so precise that they gain or lose less than a second over millions of years. You notice that by comparing clocks in different conditions on Earth, in orbit, or moving at high speed, scientists can directly observe time dilation, a fundamental prediction of relativity. The results consistently match theoretical expectations, confirming that time can be measured, manipulated, and compared with extreme accuracy. You consider the use of particle accelerators. Subatomic particles are accelerated to velocities approaching the speed of light, extending their lifetimes in accordance with relativistic time dilation. Muons, for instance, decay more slowly when moving rapidly, an effect predicted by special relativity. You notice that these experiments are not hypothetical. They are conducted routinely in accelerators around the world. Each observation reinforces the predictable interplay between motion and temporal flow, demonstrating that extreme conditions produce measurable and consistent changes in the passage of time. You explore delayed choice quantum experiments, where the sequence of measurement appears to affect outcomes in the past. In these setups, photons are split into superpositions, and the choice of measurement is delayed until after the photons have passed certain points. You notice that while results appear counterintuitive, all measurements remain consistent with quantum mechanics and causality. No information travels backward in time. Rather, correlations reflect the probabilistic nature of quantum states and their evolution. These experiments probe the fundamental structure of temporal relationships, revealing subtle aspects of time without violating physical law. You reflect on entanglement experiments and their temporal implications. Pairs of entangled particles are separated by large distances, and measurements performed on one instantaneously define the expected outcomes of the other. Timing is critical. Precise clocks ensure that measurements are synchronized, confirming that correlations occur in accordance with quantum theory. You notice that even though the particles appear connected across space, causality remains intact, and no paradoxes arise. These studies highlight the need for meticulous control of temporal parameters in testing quantum behavior. You consider high-precision clocks in orbit, such as those on satellites in the Global Positioning System. These clocks experience both special and general relativistic effects due to their velocity and position in Earth's gravitational field. Engineers correct for these relativistic time shifts to maintain accurate navigation signals. You notice that without accounting for these effects, GPS positioning would drift by several kilometers each day. Observations of time in these systems demonstrate not only the practical importance of relativity, but also the exact predictability of time under different physical conditions. You explore experiments involving ultrafast lasers and particle beams. Light pulses with durations measured in femtoseconds allow researchers to observe the evolution of atomic and molecular processes in real time. These measurements probe time intervals far shorter than human perception, revealing the precise sequence of interactions. You notice that even on these minute scales, physical laws dictate the timing of events consistently. Time remains measurable, ordered, and integral to understanding how energy and matter interact. You consider tests of temporal interference. In laboratories, photons or electrons pass through multiple paths, creating interference patterns dependent on the timing of each path. Adjusting the sequence or duration of pathways affects the resulting pattern, consistent with predictions from quantum mechanics. You notice that these results reinforce the idea that time is an active parameter governing evolution in controlled systems. Each experiment confirms the reliability of temporal measurement at microscopic scales, providing insight into the structure of time itself. You reflect on particle lifetimes in accelerator experiments. Subatomic particles such as pions and kaons are produced and monitored as they decay. Measurements of decay rates at varying speeds provide direct verification of time dilation. The agreement with theoretical predictions is exact within experimental uncertainty. You notice that these laboratory observations complement astronomical and cosmological measurements, forming a continuous understanding of time across scales. The universe exhibits a predictable, measurable flow of time, even in extreme conditions created artificially. You explore precision tests of quantum clocks. Experiments manipulate superpositions of atomic states to create clocks with unprecedented resolution. By measuring transitions between energy levels, scientists can observe the evolution of quantum states with extreme temporal precision. You notice that these experiments provide insight into the limits of measurement, the role of time in quantum evolution, and the interplay between observation and prediction. Time, while fundamentally a parameter in equations, can be probed directly, revealing its consistency and structure at microscopic scales. You consider how these laboratory experiments inform broader understanding. Observing time dilation, entanglement correlations, delayed choice effects, and ultrafast processes allows scientists to test theoretical predictions rigorously. You notice that every measurement reinforces the reliability of physical law and the predictability of temporal evolution. Even phenomena that appear counterintuitive are fully consistent with established theory, illustrating that time, though subtle and flexible in extreme conditions, remains measurable, ordered, and governed by precise principles. You reflect on the integration of techniques. From high-velocity particle beams to atomic clocks in orbit, from femtosecond lasers to entangled photons, laboratories provide controlled environments to test the flow of time. You notice that careful design, synchronization, and analysis are required to observe these effects accurately. Each experiment confirms that time behaves exactly as theory predicts, whether in the probabilistic world of quantum mechanics or the relativistic regime of near-light-speed travel. The universe's consistency extends from the laboratory to the largest scales of observation. You rest with the awareness that laboratory experiments illuminate the structure of time in ways accessible to observation and measurement. Extreme velocities, quantum interactions, and ultrafast phenomena all follow predictable rules, confirming both relativity and quantum mechanics. You notice that the precision, ingenuity, and rigor of experimental science allow the passage of time to be probed directly, without fantasy or speculation. In this understanding, your mind gently opens to the practical boundaries of time manipulation and the immense energies required to influence temporal flow, preparing you to consider the natural and technological limits inherent in the universe. You begin by observing the vast energies involved in affecting spacetime. Einstein's equations relate energy and mass to the curvature of spacetime, meaning that to create noticeable effects, immense concentrations of energy are required. You imagine compressing matter to extreme densities or generating energy fluxes equivalent to entire stars. These calculations are precise. Even modest spacetime distortions demand amounts of energy that far exceed anything currently producible in laboratories or by human engineering. The magnitude of these requirements impresses upon you the natural scale of cosmic phenomena, providing a calm sense of proportion. You consider the theoretical manipulation of wormholes. A wormhole is a solution to Einstein's equations connecting distant regions of spacetime. To hold one open, negative energy or exotic matter would be necessary. You notice that the amounts required, even for a microscopic tunnel, are beyond the total energy output of stars. Current understanding of quantum field theory allows for negative energy densities in limited contexts, but never at the scale needed to sustain a macroscopic wormhole. The precision of these constraints reassures you that physical law is consistent, and that time manipulation is fundamentally bound by energy limitations. You reflect on the relationship between mass, energy, and relativistic motion. Accelerating an object close to the speed of light requires energy that increases without bound as velocity approaches c. You notice that propelling a macroscopic object to near-light speed would demand more energy than exists in the observable universe. These calculations are straightforward and based on well-established principles of special relativity. You sense the calm clarity that comes from recognizing natural boundaries. The equations themselves define what is feasible without ambiguity. You explore the limits imposed by general relativity. To create localized regions with significant time dilation, extreme gravitational fields are needed. For example, a clock orbiting close to a neutron star experiences time more slowly than one far away. To produce similar effects artificially, mass or energy densities far greater than Earth's resources would be necessary. You notice that the universe provides natural laboratories, like black holes, where these effects occur, but technological replication is currently impossible. The laws governing energy and spacetime set absolute constraints, measurable and predictable, that define the boundaries of manipulation. You consider the thermodynamic implications. Manipulating spacetime or accelerating objects requires work, producing heat and entropy. Energy conservation, the second law of thermodynamics, and engineering limitations combine to prevent any practical method of controlling time on a large scale. You notice that even small-scale experiments, such as atomic clocks or particle accelerators, consume significant energy, and their effects are measurable but limited. This integration of relativistic, quantum, and thermodynamic constraints provides a clear framework for understanding the limits of technological intervention. You reflect on quantum field theory and vacuum energy. While certain exotic effects, like the Casimir effect, demonstrate negative energy densities on microscopic scales, their magnitude is minuscule. You notice that scaling such effects to macroscopic, time-altering applications is beyond current physical feasibility. The equations describe the effects precisely, and every measurement confirms their limitations. You sense a quiet order in this. Nature permits minor anomalies in energy densities, but prevents large-scale violations of causality or conservation laws. You examine relativistic spacecraft concepts. Hypothetical travel near light speed produces significant time dilation for passengers, effectively allowing them to skip decades or centuries relative to stationary observers. However, accelerating a spacecraft to these velocities requires energy orders of magnitude greater than currently achievable. Even the smallest crewed craft would demand fuel and propulsion systems exceeding known material capacities. You notice that this limitation is not speculation but an exact consequence of relativistic mechanics, highlighting the inherent scale of cosmic phenomena relative to human capability. You consider hypothetical manipulation of gravitational fields. Generating a localized curvature sufficient to alter temporal flow would require mass energy concentrations comparable to stars or black holes. You notice that producing and stabilizing such fields is entirely beyond engineering reach, and attempts would be constrained by the same laws that govern natural stellar and galactic structures. The universe provides extreme conditions naturally, but human-scale creation is limited by fundamental physics. Each calculation reinforces the predictability and rigidity of these boundaries. You reflect on the combined implications of these constraints. Energy requirements, mass limitations, thermodynamics, and quantum mechanics collectively define what is possible in spacetime manipulation. Even theoretical devices capable of minor temporal effects are limited to microscopic scales, far smaller than macroscopic human-scale objects. You notice that the laws of physics are internally consistent and exact, providing both opportunity and limitation. Observing these boundaries produces a calm understanding. The universe is orderly, measurable, and resistant to paradoxical or extreme manipulations. You imagine a time travel scenario involving practical energy sources. Any attempt to alter macroscopic temporal flow would require energy outputs equivalent to entire planets, stars, or larger. Even with perfect efficiency, these requirements remain inaccessible. You notice that the limits are not arbitrary. They are quantifiable and derived from fundamental physical constants. Every experiment and observation, from particle accelerators to astrophysical measurements, confirms the consistency of these constraints. You sense reassurance in the predictability of natural law. You explore precision experiments that test the limits of time dilation. Atomic clocks flown in aircraft or satellites measure tiny differences in temporal flow relative to stationary references. Particle accelerators extend lifetimes of fast-moving particles, demonstrating relativistic effects. You notice that these small-scale laboratory observations confirm theory to extraordinary precision, yet the magnitude of effect is minimal. The universe demonstrates time manipulation at an accessible scale only through extreme speed, gravity, or energy, emphasizing the disparity between theoretical possibility and technological practicality. You consider natural examples of extreme energy. Black holes, neutron stars, and the early universe exhibit spacetime curvatures and energies sufficient to produce noticeable temporal effects. You notice that these natural systems operate at scales orders of magnitude beyond human engineering, yet they are entirely consistent with physics. Understanding these systems provides insight into what is theoretically possible and simultaneously underscores the technological limitations inherent to human capability. The laws of energy and causality remain unbroken. You reflect on the broader lesson. Spacetime is a structured, predictable fabric, bound by energy, mass, and fundamental constants. While equations permit theoretical scenarios like closed time-like curves, practical realization is constrained by measurable limits. You notice that these constraints are not failures of imagination, but precise demonstrations of physical law. The universe maintains temporal order, ensuring that time is measurable, predictable, and protected by absolute physical boundaries. Observing these limits produces a calm appreciation for the natural consistency of the cosmos. You rest with the awareness that even the most powerful technology cannot yet manipulate time in any substantial way. Energy, mass, and physical law combine to define absolute boundaries. Observations from particle physics, relativity, thermodynamics, and astrophysics all converge to confirm these limits. You notice that the universe's temporal framework is both flexible under natural extremes and steadfast under technological constraints, providing a tranquil understanding of the scale and order that governs time itself. You begin by centering your awareness on the concept of direction in time. Unlike space, which can be traversed in any direction, time appears to have a distinct orientation, a past that is fixed and a future that is uncertain. This directionality is subtle yet pervasive, influencing every process from particle interactions to the evolution of galaxies. You notice that the physical foundation of this arrow of time lies in the laws of thermodynamics, particularly the second law, which governs the behavior of energy and entropy in closed systems. You consider entropy, a measure of disorder or the number of microstates consistent with a system's macroscopic configuration. In isolated systems, entropy tends to increase, providing a statistical basis for the directionality of time. You notice that this increase is not a random assertion but a predictable outcome derived from probability and the vast number of particles involved. Even when individual particles move reversibly according to classical mechanics, the collective behavior produces an irreversible flow toward higher entropy. This statistical principle underpins the one-way nature of macroscopic processes. You observe a simple system, a box containing gas particles initially confined to one side. When the barrier is removed, the gas spreads to fill the box evenly. You notice that while the motion of individual molecules is reversible according to Newton's laws, the probability of all particles spontaneously returning to one side is so minuscule that it effectively never occurs. This asymmetry is not imposed artificially but arises naturally from the vast number of microscopic possibilities. You sense a calm understanding of how microscopic reversibility contrasts with macroscopic irreversibility, producing the apparent flow of time. You reflect on heat transfer and energy dispersion. Heat flows from warmer to cooler regions, not the reverse, consistent with increasing entropy. You notice that this rule governs everything from the cooling of stars to the flow of energy in living systems. Each observation reinforces the sense that time is oriented, and that physical processes naturally evolve in one direction. The law of increasing entropy provides a gentle, measurable explanation for why the past feels fixed and the future open. You consider statistical mechanics, which links the behavior of individual particles to the overall properties of macroscopic systems. The equations predict the likelihood of different configurations, allowing the calculation of thermodynamic quantities like temperature, pressure, and entropy. You notice that these predictions are highly accurate, confirmed by laboratory experiments and astronomical observations alike. The universe behaves according to precise statistical rules, providing a clear and consistent explanation for the apparent arrow of time. You explore the connection between entropy and cosmology. The early universe was highly ordered, with matter and radiation distributed uniformly. Over time, gravitational clustering, star formation, and cosmic evolution have increased the number of accessible microstates, corresponding to higher entropy. You notice that the arrow of time on a cosmic scale mirrors the statistical tendency toward disorder, providing a consistent explanation for the temporal direction observed in stars, galaxies, and the universe as a whole. You reflect on irreversible processes beyond thermodynamics. Chemical reactions, biological aging, and radiation all follow directional patterns aligned with the arrow of time. You notice that while individual interactions at the quantum or molecular level may be reversible, the accumulation of countless events produces macroscopic irreversibility. This layered hierarchy of effects reinforces the universality of time's direction, from the smallest scales to the largest, producing a tranquil sense of order. You consider the role of measurement and observation in time's asymmetry. In quantum mechanics, the act of measurement collapses a wave function, creating a defined outcome from probabilistic possibilities. You notice that while the underlying equations are time-symmetric, the process of observation introduces an effective temporal direction. This subtle effect is fully consistent with theory and experiment, illustrating how temporal order emerges naturally even in systems governed by reversible laws. You observe examples in astronomy. Supernova explosions release energy in ways that cannot spontaneously reverse. Stars evolve from formation to fusion-powered maturity to collapse in predictable sequences. You notice that these processes exemplify macroscopic irreversibility, consistent with increasing entropy. Time's arrow is embedded in the life cycles of celestial objects, offering a clear demonstration of directional flow across vast scales. The consistency between microscopic statistical rules and cosmic evolution reinforces the deep interconnection of time and entropy. You reflect on the psychological perception of time. Human memory records the past but cannot access the future, a direct consequence of physical asymmetry. You notice that this aligns with the increasing entropy of the brain's processes and the environment. The sense of a flowing present with a defined past and open future is mirrored by the universal statistical tendency toward disorder. This connection provides a calm understanding of why your experience of time aligns with physical reality. You explore the concept of microscopic reversibility. At the level of atoms and fundamental particles, the equations of motion are symmetric with respect to time. You notice that if you could track every particle, its trajectory could be reversed without violating the laws of physics. Yet, the statistical improbability of coordinated reversal for large systems ensures that macroscopic phenomena remain effectively irreversible. This contrast between microscopic reversibility and macroscopic irreversibility is central to understanding the arrow of time, demonstrating the subtle interplay of scale and probability. You consider fluctuations in entropy. While temporary local decreases in entropy are possible, they are exceedingly rare and temporary in macroscopic systems. You notice that over billions of years, stars, planets, and galaxies have evolved consistently toward higher entropy, with any local reductions having negligible effect on the overall temporal direction. Observing these statistical tendencies produces a calm sense of order, confirming that time's flow is robust, measurable, and predictable. You reflect on information theory and entropy. Information loss in processes such as mixing, diffusion, and radiation corresponds to an increase in entropy, linking the abstract concept of information to physical time. You notice that these principles are used in calculations ranging from thermodynamic engines to cosmological models, reinforcing the universality of the arrow of time. The coherence between physical, statistical, and informational measures provides reassurance of the predictable structure of temporal flow. You rest with the awareness that time's direction emerges naturally from the laws of physics. Entropy, statistical mechanics, thermodynamics, and observation collectively produce the arrow of time. Microscopic laws are reversible, yet macroscopic processes follow a consistent forward flow, aligning your perception with universal patterns. You notice that this flow governs the evolution of stars, galaxies, particles, and life itself, producing a calm appreciation for the stability, predictability, and order of time in the universe. You begin by directing your attention outward, toward the stars and galaxies that fill the night sky. Light traveling from these distant objects takes time to reach your eyes, providing a window into the past. When you observe a star 100 light-years away, the photons arriving at your location began their journey a century ago. You notice that this natural delay allows the universe to act as a vast time machine, preserving the history of distant regions for careful study. Every photon carries information about conditions long before it entered your observation point. You consider spectroscopy a fundamental tool in astrophysics. By analyzing the wavelengths of light from stars, nebulae, and galaxies, scientists can determine their composition, temperature, motion, and age. You notice that spectral lines shift due to the Doppler effect, revealing whether objects are moving toward or away from you. These measurements provide detailed insights into stellar evolution and cosmic expansion. Each observation is a direct record of the past, encoded in light, allowing you to reconstruct events without altering them. You reflect on pulsars, rapidly rotating neutron stars emitting beams of radiation at precise intervals. By timing these pulses, astronomers can measure distances, detect gravitational waves, and observe minute changes in rotation. You notice that the signals arriving now were emitted thousands or millions of years ago. Each pulse acts as a timestamp, a marker of past activity preserved across space. Monitoring these precise clocks provides insights into processes occurring long before the present moment, allowing you to read the history of extreme astrophysical objects. You explore the cosmic microwave background (CMB), the afterglow of the Big Bang. This faint radiation fills the universe and carries information about conditions roughly 380,000 years after the initial expansion. You notice that by studying the variations in the CMB's temperature and polarization, scientists can infer the distribution of matter and the processes shaping the early universe. The photons reaching you now represent a direct observation of primordial conditions, giving access to a formative epoch that no living observer could have witnessed. You consider the method of light echo observation. Some supernovae and variable stars illuminate surrounding interstellar dust, creating reflections that reach Earth years or decades later. By studying these echoes, astronomers can reconstruct events with temporal precision, mapping the timing and sequence of cosmic phenomena. You notice that these observations are not speculative. They provide concrete measurements, allowing you to witness the unfolding of astrophysical events long after they occurred. The universe preserves its history in measurable, retrievable forms. You reflect on galactic archaeology. By observing populations of stars in clusters and galaxies, scientists can determine ages, chemical abundances, and evolutionary histories. You notice that older stars contain fewer heavy elements, revealing the gradual enrichment of the universe through successive generations of stellar fusion. This record provides a chronological framework, showing how galaxies evolved over billions of years. The information is encoded in starlight, measurable through well-established observational techniques, giving you a precise understanding of the past. You examine time delays in gravitational lensing. Massive objects, like galaxy clusters, bend the path of light, producing multiple images of background objects. You notice that these images reach Earth at slightly different times due to differences in path length. By measuring the time delays, astronomers can determine distances, infer mass distributions, and study cosmic expansion. These observations are a direct record of past light paths, allowing you to reconstruct events that occurred millions or even billions of years ago. You explore the role of supernova remnants. Explosions leave behind expanding shells of gas and dust, which continue to evolve over millennia. You notice that observing the current structure provides information about the original explosion and the progenitor star. By measuring velocities, chemical composition, and emission spectra, scientists reconstruct the history of these events. The remnants act as historical archives, demonstrating that even destructive phenomena are preserved as readable signals of the past. You consider pulsar timing arrays, which detect minuscule fluctuations in the arrival times of pulses caused by gravitational waves. You notice that these measurements allow scientists to observe events in spacetime itself, such as the merging of supermassive black holes, long after they occurred. Each tiny variation in timing encodes information about cosmic events in the past, providing access to phenomena beyond direct visual observation. The universe continuously records its history in ways that are measurable, precise, and predictable. You reflect on neutrinos and cosmic rays, particles traveling across vast distances almost unimpeded. You notice that these particles provide information about the cores of stars, supernovae, and distant cosmic sources. Unlike light, neutrinos interact very weakly with matter, allowing them to reach Earth after traveling immense distances without scattering. Their arrival carries details of processes that occurred millions of years ago, providing an alternative record of cosmic history that complements electromagnetic observations. You consider the integration of observational techniques. By combining spectroscopy, pulsar timing, gravitational lensing, CMB analysis, and particle detection, scientists can reconstruct events across cosmic time with remarkable precision. You notice that each method is grounded in measurable physical properties and well-established theory. Together, they allow a continuous reading of the universe's past, giving you a comprehensive view of how stars, galaxies, and structures evolved over billions of years. You rest with the awareness that while physical time travel remains beyond reach, observation allows you to experience the past with clarity. Light, radiation, particles, and gravitational effects preserve information that reaches you across space and time. You notice that the universe itself maintains a meticulous record, accessible through careful measurement and analysis. Each observation deepens your understanding, demonstrating that history is not lost, and that the cosmos offers a serene and reliable archive of events long before your own moment in time. You begin by gathering the threads of everything you have observed about time. From the steady oscillations of atomic clocks to the behavior of fast-moving particles, from the distant light of galaxies to the precise ticking of pulsars, you notice a coherent and consistent structure underlying temporal experience. Time is measurable, ordered, and predictable within the laws of physics. The principles of relativity ensure that clocks in motion or near gravitational masses behave precisely as predicted. Quantum mechanics provides probabilistic rules that govern the smallest scales without violating causality. You consider the combination of relativity and energy constraints. Manipulating spacetime requires energy far beyond human capability, whether attempting extreme velocities, warping gravitational fields, or creating hypothetical wormholes. You notice that these limitations are exact consequences of mathematical and physical law, not arbitrary restrictions. Each equation describing mass, energy, and curvature defines boundaries that cannot be violated. This recognition brings a gentle reassurance. The universe is orderly, its temporal fabric robust, and the rules that govern it precise and unchanging. You reflect on causality and logical consistency. Paradoxes, like those imagined in thought experiments, are prevented by fundamental constraints. The universe's structure enforces self-consistency, ensuring that effects cannot precede causes in ways that would produce contradictions. You notice that principles such as the Novikov self-consistency condition, alongside constraints from energy and spacetime geometry, preserve the reliability of historical sequences. The laws of physics provide a natural safeguard against inconsistencies, a quiet assurance that the flow of events remains stable and coherent. You consider time on microscopic scales. In quantum systems, the probabilistic nature of particles and their interactions illustrates that time can appear flexible, yet causality is never violated. Experiments with entanglement, delayed choice setups, and ultrafast measurements reveal subtle correlations that confirm theoretical predictions. You notice that even in these realms, time is a parameter that can be precisely measured and analyzed. The microscopic world behaves in a way that complements and supports the macroscopic arrow of time, producing continuity across scales. You reflect on entropy and the arrow of time. The increase of entropy provides a statistical foundation for why time flows forward and why the past is fixed while the future is open. Stars age, galaxies evolve, and planetary systems develop in accordance with predictable thermodynamic trends. You notice that microscopic reversibility does not contradict the macroscopic directionality of time, but rather underlies it. Observing the universe's evolution, you feel a calm understanding that time is a continuous, ordered sequence shaped by statistical regularities and physical law. You think about observing the past through light and other signals. Photons, neutrinos, and gravitational waves reach you from distant stars, galaxies, and cosmic events, providing a direct record of history. You notice that the universe preserves information about its own past with remarkable fidelity, allowing you to study events long before your own existence. Spectroscopy, pulsar timing, cosmic microwave background measurements, and gravitational lensing collectively provide tools to reconstruct cosmic history. Observation becomes a means of traversing time safely, without contradiction, revealing the universe's evolution in precise detail. You reflect on the integration of all these insights. Time is a dimension intertwined with space, governed by relativity, constrained by energy, shaped by causality, and statistically oriented by entropy. At quantum scales, it provides a parameter for evolution, while at cosmic scales, it allows the reconstruction of events billions of years ago. You notice that these perspectives complement each other, producing a consistent understanding of temporal structure. The universe is orderly, predictable, and accessible to careful measurement, offering a sense of calm comprehension. You consider technological boundaries. While theoretical concepts like time loops or extreme relativistic travel are mathematically valid, the energy, mass, and stability requirements make them unreachable with current capabilities. You notice that this limitation is not a failure of imagination but a precise manifestation of physical law. Understanding these boundaries provides a serene awareness that the universe maintains internal consistency and prevents violations of temporal logic, offering security in the predictability of natural processes. You reflect on the interplay of measurement and observation. Atomic clocks, particle accelerators, and space-based detectors allow the exploration of time with extraordinary precision. Each measurement confirms theory, from relativistic time dilation to quantum correlations. You notice that empirical study provides both insight and reassurance. The universe behaves in accordance with predictable principles, and every experimental result reinforces the reliability of temporal structure. Knowledge of these facts produces a calm sense of order and stability. You think about your own perception of time. Human experience is aligned with physical reality. Memory records the past, the present unfolds continuously, and the future remains open. You notice that this subjective experience is consistent with objective measurements, from thermodynamic trends to astronomical observation. The coherence between perception, physical law, and experimental data creates a tranquil understanding that time is unified, measurable, and logically ordered across all scales of existence. You consider speculative but physically grounded possibilities. High-speed travel produces measurable time dilation. Gravitational extremes affect the passage of time. Quantum systems reveal correlations across time intervals. You notice that while these effects are real and observable, They remain constrained by energy, mass, and fundamental constants. The universe allows exploration and study without permitting violations of causality or paradoxical outcomes. This realization reinforces the notion that time is both flexible in extreme conditions and rigorously consistent in all observed phenomena. You reflect on the cumulative picture. Relativity, quantum mechanics, thermodynamics, observational astronomy, and experimental physics together form a coherent framework. Time is measurable, directional, causally consistent, and accessible through precise observation. You notice that each layer of understanding adds clarity without contradiction. The universe maintains integrity across scales, providing both the opportunity to explore temporal phenomena and the assurance that fundamental laws remain unbroken. You rest with the awareness that the nature of time is accessible to careful study and precise measurement. While human-scale time travel remains impossible, observation, calculation, and experimentation reveal the structure, direction, and constraints of temporal flow. You notice that the universe is orderly, consistent, and predictable, offering a calm confidence in the stability of all events. The integration of relativity, quantum theory, causality, and cosmic observation leaves your mind gently attentive to the elegance and rigor of time, preparing it to rest peacefully.